So I'm going to tell you about a project that pretty much took up most of my life for about 5 years, which is Astrobee on here. So here's a picture of Astrobee on the International Space Station. Astrobee is a new generation of robotic free flyers that operates inside the International Space Station and works together with astronauts. Our project started in late 2014. 3 Astrobees arrived on station in 2019, and we've begun on-orbit operations. So what you see here is Bumble, which is the first bee that we commissioned on orbit and sitting on its docking station. That's this silver box here with the AR targets. I'm going to give you a little bit of background about Astrobee. Really, our heritage is with these free flyers that have been on board space station since 2006 called Spheres. The Spheres facility is run out of Ames Research Center, which is where the Astrobee project was executed. They were built by MIT and have been pretty much the most used facility on board ISS since they've been there. They run off of CO2 cartridges or canisters, which you can kind of see the ends of here sticking out. And they're used by guest scientists to test out their technologies in zero-G in a fairly benign environment in zero-G. They're shirt sleeve environment with astronauts. Things can be rescued by crew. So it's a good way it's a really great zero-G test bed. However, Spheres has several important limitations. One is that they have to have crew supervision at all times, primarily for safety reasons. For example, some of the materials, the plastics, for instance, on Spheres are flammable, and so we can't have a flaming ball floating around in the space station, so crew has to watch it at all times. Also, for each activity, there's quite a bit of setup and teardown involved. The robots, or these little Spheres, satellites don't automatically recharge or dock, and they when they're not in use, they're in a stowage locker. So crew has to go get them out of stowage, put in fresh CO2 canisters, put in fresh batteries, and then during the activity also replenish those as they run out. And then finally, the Spheres navigate using ultrasonic beacons that are set up in a 2 meter by 2 meter by 2 meter volume within a single module in the space station. And so that really limits their utility for activities other than simple scientific experiments. We can't navigate outside of that volume and visit other modules. Also, they've been on orbit for over a decade, and they're really starting to show their age. So, for instance, the onboard processors are extremely limited. I mean, we're talking like 2004 technology here. And then also things like the nozzles are starting to fail. So it really, while Spheres has been extremely successful, it really is time for an upgrade. And so that upgrade is Astrobee, which we see here. This was on July 30th of 2019 when astronaut Anne McLean unpacked the first Astrobee. Again, this is Bumble. You can tell because it's blue, they're color-coded. And the Astrobees are designed to overcome a lot of those limitations of Spheres and add some additional capabilities. So we've actually passed about a year of operations on orbit. The goals of the project were to deliver 3 new free flyers and a docking station to the ISS to replace the Spheres. And so the goal is to enable guest science, and I'll be talking a little bit about some of the capabilities we have on board to enable guest science. But also to look at how these free flyers can make on-orbit operations more efficient. So to demonstrate feasibility of using these types of free-flying robots for caretaking of future vehicles, and also to help automation of certain ISS operations. Excuse me. What you see here in the image is our 3 flight robots. We have Queen, which is green, Honey is yellow and Bumble is blue, and then a few other pieces of equipment such as perching arms and batteries. So our technical approach was really guided by our experience with spheres. We used our lessons learned from spheres to set our objectives. For instance, we want to minimize the burden on astronauts. We want to execute most of our experiments fully autonomously with ground supervision. So as before, every sphere's activity had to be completely monitored by crew. We wanted to free up crew time when we operate Astrobee. Also, as I mentioned, spheres had consumables that had to be resupplied by the astronauts. And so we designed Astrobee to be battery powered, and also enabled it to autonomously dock and recharge, so that we wouldn't need astronauts to resupply consumables. We also incorporate a bunch of safety controls, such as collision mitigation and use of non-flammable materials, so that, again, we free up astronaut time, not requiring their supervision. And finally, we use vision-based navigation systems so that we're not confined to a small volume that needs, for instance, external beacons, and we don't require any new infrastructure in the ISS interior. And that really opened up the U.S. orbital segment to us. Actually, I'm gonna, for smoothness, I think it works better if I show this video separately. Do full screen here. Okay, so this video shows a little bit of an overview of the first 4 years of our development. So we developed the Astrobee using a series of prototypes, and you can see some of our early propulsion systems there. This is the current propulsion system, and we tested on a granite table in our lab at Ames Research Center. This is the only way that can really test the propulsion system here on Earth. Obviously, though, we can only work in 2 degrees, or two axes and 3 degrees of freedom. We're testing out, here's a perching arm, some of the flight software, including our control systems. This is the user interface, some of our simulation and visualization, where we're simulating ISS operations. We did a bunch of testing, again, on the granite table with some other payloads. That's a gecko gripper by Stanford. Here we're looking at updating inertial properties by moving a payload mass. Here's one of our first docks. It's a certification unit. And then just a quick artist concept of how we originally envisioned Astrobee operating on space station, for instance, moving cargo. Okay, I'm going to skip the credits here. Switch back. Okay, so I'm going to give a quick system overview. I'll talk about some of the major subsystems of Astrobee, and then I'll go into a little more depth on a few of the enabling technologies, such as propulsion and visual navigation and human-robot interaction. So what we see here are Astrobee's operational system elements. The on-orbit portion are these 2 here, the 3 free flyers and the docking station. And then we have a ground data system that includes control stations and some additional tools. In addition to these flight elements, we also have ground testing systems and labs that are all part of the facility. So there's a lot here. I won't go into too much detail on the propulsion system because I've got another section of the talk that I'll go into more depth on. But Astrobee is basically a sandwich with 2 propulsion modules on either side and the central avionics section. The avionics section includes the main processors and most of the sensors, for instance, the cameras. We also have touch screen. I'll talk about the HRI interfaces a little bit later. We have these open areas. This is part of how we're accommodating guest scientists. Open areas at the bottom and then the top. We see the arm installed here, but this can be an open area as well, that are payload bays where guest scientists can plug in hardware. And then we have a USB interface to the main processors. The robot is a 32 centimeter cube. It's about, without any payload, so no arm and with only 2 batteries, it's about 9 kilos. The arm is about 1 kilo. We use 3 smartphone computers. I'll talk about that more a little bit later. Let's see what else. Oh, the skin here is actually removable, so we can put different labeling on here. And I think that's about it on here. So I'll cover for now. The way that Astrobee communicates is when it's flying around on station, it uses the station Wi-Fi, and that's just a standard Wi-Fi. However, when it's on the dock, we actually have an Ethernet connection to the ISS payload LAN. We have a single telemetry stream down to the ground, not shown here, but this actually goes through the TDRS geosynchronous satellite system that's used to communicate with ISS. And then from there, we relay through Marshall Space Flight Center in Huntsville, Alabama, out to various control centers. I'll talk a little bit about that later, but our main one, of course, is here at Ames. And then we also have a data archive where we use that to distribute the collected data out to the guest scientists. Also, if we have large file transfer needs, for instance, if we've been flying around on some long sorties, running our cameras, it's usually a whole bunch of data. We can actually stage that to the dock or to the ISS NAS storage for later downlink, because that can take, it's a shared pipe here with a bunch of other payloads and ISS operations, so it can often take days to actually get all your data down to the ground. Our onboard computing, we have 3 main processors. It's a layered approach, and we do that in order to isolate software to attempt to provide some robustness. We use a service-oriented architecture. It's built on the robot operating system called ROS. That's an open source system, a standard that's used by quite a bit of the robotics research community. At the lowest level, we have our low-level processor. This is where we run all the high-rate control in isolation from the rest of the software, and we're running Linux on that processor. The mid-level processor is where most of the infrastructure software runs, for instance, the visual navigation system. That's on an Inforce board, also running Linux. And then at the top level, we have our high-level processor, which is where we expect most guest science to run as an Android app. And this also runs some of our human robot interface affordances, for instance, the touchscreen interaction, and it also does the HD video compression. And then there's microcontrollers all over the robot, used for power management, control various parts of the prop modules, and the perching arm, and those are our PIC microcontrollers. We see here the perching arm. This is about a 1 kilo payload that's designed to grasp the handrails that are all over the station that are used by crew. That's how they move around the station. And the idea here is that we can use this to hold onto a rail and turn off the prop modules and save a little bit of energy when we need to dwell for any duration in a single place. Once it's perched, the arm can actually be used as a pan tilt unit. So we have an HD camera that points out the front of Astrobee. And so by using the 2 joints in the arm, we can pan and we can tilt. The arm is designed to be safe for crew to use as well. It can be used manually, so crew can actually perch the robot on a handrail themselves, and this is in case they need to get past Astrobee quickly, you know, there's some emergency and they want to move it out of the way, they can actually just grab it, stick it to a handrail, and it's out of the way. The design is also modular, so this gripper is removable by crew on orbit. So for instance, Stanford has developed a gecko-inspired gripper that has been launched and is waiting installation on board Space Station right now. So crew can actually, there's just a couple of captured screws, and they can just unscrew it and stick on the Stanford gripper. This is our docking station. You saw a picture of this a little bit earlier. The docking station has 2 berths. This is where the Astrobee sits. As you can see, I mentioned we have 3 Astrobees on orbit. We can only berth 2 at a time, though. The third one would have to stay in stowage, and so if we ever need to use 3 at once, crew would have to go fetch it out of stowage and plug in some batteries. The robot, when it's docking, uses these AR targets to achieve a more precise alignment with these the berths. So we see the cones here. They're part of the docking system. And then we have these 20-pin connectors that provide power and Ethernet. We have a pretty flexible mounting system. You can see the ends of the brackets here. These extend all the way up the back side of the dock, where we can put different mounting brackets on here to accommodate where they need to put us in ISS. No place is safe. You may be assigned one spot for a while, but then they can move you as well. So if they need to reconfigure, and so we gave ourselves some flexibility by providing this modular mounting system. The basic Conops for Astrobee is that when it's idle, it just sits on the dock and charges. Astrobees can execute very complex plans with full autonomy, no need for astronauts, but they would be supervised by a ground operator. Astrobee's current behavior when it encounters an anomaly is to stop and wait for operator intervention. This was primarily an issue of the project scope. We have the hooks and the eyes in there for adding additional behaviors and anomaly handling, but that was not part of the scope of the original project. It can continue to operate even when we have comm outages, which happen quite often throughout the day on ISS. For instance, when there's a handover between the satellites, the TDRS satellites, there's a small loss of signal. Astrobee, if it's executing a plan, will continue to do so. And then again, if it encounters an anomaly while it's in LOS, it will just wait until we get AOS, acquisition of signal, and the operator can come in and intervene. The operator can take over and teleop at any time. So we have additional controls in the ground control station that enable that. And astronauts can also be operators, but we really don't foresee this as being a common occurrence. The whole objective of Astrobee was to minimize crew time. However, we do anticipate that there may be future HRI researchers who might want to actually interact with crew more and might then want crew to be an operator of Astrobee. So our hardware status is that all our planned on-orbit hardware is aboard the ISS. We also have a flight spare B and flight spare dock that are in Houston in the bonded stores. So if at any time we need to bring down a piece of equipment, we can launch a replacement. We got that equipment up to orbit through 4 launches, starting in late 2018. That's when we sent up the docking station. And then we sent 2 Bs with 8 batteries apiece. And some spares back in April of 19. And then the third B and its associated batteries plus the 3 perching arms for each B went up in July. So in addition to the flight hardware, the Astrobee facility has 2 ground free flyers, 1 ground dock, and lots of spare parts. So when we built the robots, we built or purchased enough parts to build 10. But we only completely assembled 6, and so we have lots of spare parts that we can replace and repair. So Astrobee is designed to fly inside the ISS only. I mean, it'd be great if we could fly in both environments. However, due to various constraints, it was decided very early on that we would concentrate on the IV environment. Some of the considerations you see here, for instance, safety. If you have a malfunctioning EV flyer, there's lots of room to build up speed, and we could cause some serious damage to the station. So that just entails a whole lot more design constraints. Also for utility, the propulsion system would require some sort of reaction mass, and so we'd have to deal with refueling, probably shorter sortie durations, and then finally cost. We want to be able to use some cheap, capable, commercial off-the-shelf hardware components, and those are generally not EV compatible. They usually can't stand up to the vacuum or extreme temperatures of the EV environment. So this is the propulsion system. This is one of the two propulsion modules that sits on an Astrobee. You're seeing it here with the skin removed. So because it's all electric, that really simplifies our recharge. The two modules are interchangeable, so they can be swapped to either side. And this is nice because this way we can fly a single spare propulsion module to orbit, and it can replace any module on any B that has a malfunction. It has a central impeller behind the screen here. The two impellers counter-rotate, so that cancels torque. Our max acceleration is 10 centimeters per second squared. And again, because we are in the cabin with astronauts, we have to consider safety. And so all the moving parts are enclosed and behind some sort of screen or cover. So for instance, the impellers are behind this fine screen here. This was fine. We actually had to do tests to make sure we wouldn't suck in astronaut hair. And so that it's the inflow there. And then the nozzles, which we see here, there's one on each side of this propulsion module, and then two on this outer face, have these grills, and those both help to shape the flow coming out of the nozzle, but they also keep astronaut fingers out of the nozzles. We also have these bumpers on the corners, and then there's a thin layer of padding. This white part here is a little bit of foam that covers this. There's this metal cover here. So when we were designing the propulsion, we considered a couple of different types of systems. For instance, we looked at the spheres system, which uses a cold gas system. There's, of course, a big limitation of that is that you have a limited amount of reaction mass. And so when we did design, when we went with fans, we have now an unlimited amount of reaction mass. Also, we're not adding any gases to the cabin air. So, I mean, this is a small amount of CO2, and there are already CO2 scrubbers on the ISS, but still, it's a consideration. So once we went with that decision, we have these sort of cascading design implications. Now that we have unlimited reaction mass, what we're trying to really look at really improve is the power efficiency. And so for improved power efficiency, you want a low exhaust velocity. And that then has implications for things like the nozzle area. So for instance, with the high exhaust velocity, we have really tiny nozzles on the spheres, but on Astrobee, it's approximately 10% of the surface area. But there are other advantages as well. For instance, the low max pressure means that it's a very safe system. This made for very good demonstrations and discussions with the safety panel, where we can show that it's all low pressure. This is a diagram that shows you how the air flows within the propulsion module. So here the cover is now removed. So it's built around this plenum, you can see in here. The centrifugal impeller pulls the cabin air in. lightly pressurizes the plenum, and it's very light pressure. We're talking 0.1 psi over the ambient cabin pressure. And then the air flows out of the 6 nozzles, so 2 on the Y face, and then 1 each around on the other sides. We have 12 nozzles in all, and this provides us with holonomic control, so the robot can move in any direction and about any axis instantaneously. As I mentioned earlier, we cancel out the gyroscopic moment and the drag torque by having the impellers rotate in opposite directions. The nozzles, which I pointed out earlier, they blow air in a fixed direction, so it's not directed really, and you control just how wide you open these flappers to adjust the thrust. So here we see the closed position, partially open, and then fully open. I mentioned the grills here, which give a little bit of shaping to that flow and keep astronaut fingers out. We have the servo and gearbox in here. So for holonomic control, none of the thrust vectors pass through the robot center of mass. So use matched pairs to provide a pure force along an axis or a pure torque about an axis. We also have non-symmetric performance on those faces. So for instance, the hazard camera, which is right here, I'll talk about this a little bit later, is a time of flight camera, faces forward. And so forward is our preferred flight direction. If you know that it's clear on other faces of the robot, you can fly in those directions. But generally, if you want the robot to fly autonomously, you want it looking out for obstacles. So that's our preferred direction of flight. Okay, so now vision-based navigation. So I mentioned one of the sphere's biggest limitations was that it could only fly in a 2-meter cube volume in a single module due to the need for the ultrasonic beacons for navigation. So when we designed Astrobee, we didn't want to have to add any additional infrastructure to navigate. And that would lower our impact on station operations and also open up the whole USOS to Astrobee. All we need to do is build maps. The built-in external sensors are primarily cameras. We have 3 facing forward, 2 facing aft, and 1 facing up. Our primary navigational camera is this wide-angle nav cam used for our general purpose navigation. And then the rear-facing dock cam that's used for the AR, fiducial relative docking, localization for docking. We also have 2 time-of-flight sensors. One is this HAZ cam and then the perch cam. The perch cam is used to do handrail relative navigation when we go to perch. The speed cam is a redundant velocity sensor used for safety reasons. It looks at the overhead and will cut off propulsion if Astrobee exceeds threshold. And then the final camera is what we call the SciCam or science camera, and that's an HD streaming camera. We have several modes that we run for position estimation. They all use an augmented state extend Kalman filter. They just feed different features into that filter. And they use the gyroscope and accelerometer from the IMU. So the general purpose navigation is used throughout the ISS, does not require any infrastructure, and it runs at about 2 hertz. We can get about 5 centimeters of accuracy just generally. However, there are actually parts of the ISS where we can improve that and get more on the order of 1 to 2 centimeters. And those are in areas where there's a lot of features, where it's feature rich. The 5 centimeter performance is more for places like down near the deck of the ISS, which is generally kept fairly clear, which of course means there's fewer features there to track. We also run simultaneously a 6 hertz optical flow system. And this allows us to continue to navigate in areas where we don't have a lot of features. So for instance, if we wander into an area where we don't have an existing map, this gives us a sufficient capability to move back into an area where we can better localize ourselves. The fiducial relative system is used in the vicinity of the dock. So this gives us about 1 centimeter accuracy localization, and it uses this fiducial tracking system. We can also designate other workspaces and other parts of the ISS if we need that higher accuracy, higher navigation performance. If we put up AR targets where we have, have astronauts put up additional AR targets in a work area, we can use that then to gain some additional navigation performance. And then finally, the perch relative mode that we use for perching in the vicinity of a handrail. It uses that time of flight sensor and uses the 3D point clouds to estimate where the rail is, and we get about 2 centimeters of accuracy in that system. So our main navigation system is this the Sparse feature tracker, and we first develop a map. We do that offline. What you see here are a couple of examples of those sparse maps. So this one here in the back is our a map of our granite lab at Ames. You can see here the surface of the granite table. And this frame here, since this is also used to test spheres, so this frame here holds those external ultrasonic beacons. So you can kind of see some of the features here of that granite lab. And then we see here a sparse map of the Japanese experiment module, which is where the Astrobee dock is located. So these maps consist of interest point descriptors, and then also those location estimates that you see here. The way that we build the map is first we collect a bunch of images from different perspectives, and then we detect surf features on that. So the surf is speeded up robust features. We then match features between image pairs and track them between those multiple images. From that, we can triangulate the initial camera pose and the interest point location. So you see here an example of some visual features within our granite lab at Ames. We then simultaneously solve for 3D positions of those tracked features and camera poses. We use an incremental bundle adjustment, and then do a global bundle adjustment to remove outlier interest points. Finally, we rebuild the map with those known camera poses, and we switch to a brisk feature, which is binary robust invariant scalable key points, and then register with fixed coordinate frames. So it's very easy to do that in our lab. We can measure where things are, so it's pretty easy for us to register that. On the ISS, we do have a few points. It's actually harder to get some quote-unquote ground truth for some locations on the ISS, but there are a few that are known, and so we use those to register the map to the ISS reference frame. And then finally, we build a bag of words database to allow us to quickly search for similar images. So in our case, the image features are the words in the bag of words database. So then the way we actually use the system to localize for the sparse map is we then detect those brisk features as we're flying around. We look for similar images in the bag of words database. Then we use ransack to find the matches, and then send those pixel coordinates and 3D positions to the EKF. Similarly, for the AR target localization, we use the corners of the AR targets to the EKF, just like we would the sparse map features. And then in the case of handrails, we detect features of the handrail using the depth sensor, and then pass those along to the EKF. I mentioned the optical flow. We use Lucas Canade in order to do the optical flow, and we do backwards tracking to remove the outliers. The way the EKF works is, I mentioned it's an augmented air state EKF. We send a registration pulse to the EKF when we capture an image. The EKF runs at about 62 hertz. Oops, sorry. Runs about 62 hertz, but the image processing process takes much longer than that. It runs at about 1 to 2 hertz. So the registration pulse allows the EKF to continue running, and then once the image processing is complete, we can then do an update of the EKF. It basically lets it backtrack and rewind to where that image was taken to sync that data properly. Okay, moving on to human interfaces. So we do fly in space station with astronauts, and so we need to be good crew members. So we really we had some high-level goals for developing the human interfaces. It was not a big part of the project. The scope of the project kind of prohibited us from doing a lot of work in HRI, but we wanted to provide enough infrastructure there to make improvements as Astrobee continues to operate on orbit. So one goal was to make it easy to operate and to require minimal training for ground operators. When we were developing Astrobee, we talked to ISS flight directors about using a free-flying robot on orbit. And they basically told us that they wouldn't use the system if they had to certify a new flight controller position. So, because a flight controller position takes a lot of training, a lot of work and it's basically a huge cost to the flight operations directorate to certify new position. So we really wanted to design Astrobee to be something that would take minimal training. We set a limit that we said we want to take no more than 2 hours to learn how to at least minimally operate an Astrobee. Also, we wanted to enable future HRI research. So we wanted to provide that basic infrastructure that would let those future guest scientists experiment with how the robot could communicate with crew. And then finally, as I mentioned, we want to be good crewmates. So we thought hard about how crew, who often only have one hand free, could physically interact with the system. For instance, we looked at handholds. How can they actually grab the robot? Swapping batteries, swapping payloads. So a lot of effort went into designing interfaces for that. So this is a little overview of our ground data system. This is the other way that humans interact with the robot from the ground. This is our primary way of interacting with the robot. So we have a Astrobee control station, see right here. It has a sortie planning tool. That's what we're showing here, that allows a user to set waypoints and activities for the robot, basically create a plan that the robot will run. We have execution monitoring, so we send live telemetry, image and video streams, and we have this 3D virtual display that displays a robot from telemetry. We can run plans or send single commands, so we have a teleop capability that lets the user send single commands to, for instance, move to a specific position or deploy a payload, for instance, the arm, and so very small granularity control. There is a crew control version of the station. We don't expect to use it very often. And it runs on an Express laptop computer on board the space station. Also on the ground, we have a server that we use for archiving and distributing the Astrobee data. And we have a suite of engineering tools to support maintenance and software upgrades. We actually have the crew operator training videos available to the public. If you go to this location here, this URL, you can actually take the crew training for operating the Astrobee using the crew interface. When we designed the interface, we envisioned 3 levels of operator capability. So there's crew, which, as I mentioned, is just this 20-minute training video that they can take on board. It can run plans that are developed by guest scientists. They would then run those plans and deal with any contingencies using teleop. But they can't build plans themselves, so that is not enabled in the crew interface. We have had discussions where we may regret this in the future because there are some astronauts who really like to run their own experiments on weekends, and we have a feeling that some of them might want to play with Astrobee on the weekends, but they'll be able to teleop, but they won't be able to create plans to do that. The next level up would be an operator. So for instance, that would be a flight controller in Houston or a payload controller in Huntsville. And these are not expert users. So they'll have some familiarity with the system, and we have about 2 hours of training involved. But they aren't experts at it. And so they have basically the same interface as the crew with the one addition of the planning tool. And then finally, the top level is engineering level controller. And so these are expert users. So that would be Astrobee developers and facility engineers or guest scientists they've really become familiar with large portions of the system. And so for that interface, there's a whole bunch of other tabs available that give them a deeper control and more telemetry that they can use to monitor subsystems. Astrobee can control from pretty much anywhere. Flight controllers at Mission Control Center in Houston, payload controllers at POIC in Marshall, guest scientists at Ames or in their home institutions. We've actually, during COVID-19, during the shelter in place, we've actually started interacting with the on-orbit hardware from home. We've had a couple of sessions where we've controlled the dock and Astrobees from the pilot's home. And last month, JAXA controlled Bumble from Japan. So we're really proving out that we can control these robots from anywhere. We do have, as I mentioned, some infrastructure here for human-robot interaction. What you're seeing here on the left is a little animation that shows you what these eyes that we have on the robot do. It's just animation, but there are some links to things happening on board. So for instance, we have these ideas of like showing direction, giving the crew some idea of the intent of the robot. So for instance, which direction the robot is going to turn or move. We have signal lights on the propulsion modules. We can do different sequences on those lights, again, to show the intent of the robot. There is a speaker and a microphone. However, the microphone is not currently enabled. There's really 2 reasons. One is that right now we don't really need the mic. But the other is that actually crew is a little bit concerned about having live mics on board the station. It's a crew privacy issue. So and it's kind of strange because they're actually a little more concerned about live mics than they are about live cameras, but because they're used to live cameras, but they're not so used to live mics. So we do have a set of indicators for crew that show whether cameras are on, whether they're streaming down to the ground, and then whether a microphone is on. We actually use blue as a reserved. We have blue as a reserved color for Astrobee that indicates that a mic's on. So we have the same set of these indicators on the aft side, and then also on the propulsion modules. We'll light up a single one of these signal lights blue as well, so that pretty much from any direction you can see whether there's a mic on or not. We also have this touchscreen, so guest scientists can actually put Android apps on and interact with crew that way. We have a laser pointer that lets lets the robot point at things to, again, indicate things for crew. If you want to say, oh, look at this thing over here, and turn on the laser pointer. Also, one of our first guest scientists is JAXA. They're running a programming contest. They'll have students program Astrobee to navigate to a specific location and point at a target using the laser pointer. And they have to like snap a picture that shows where they hit the target. And then there's a couple of other indicator lights and flashlights as well. Okay, so I'm just going to close. And let me again do this from the external with a highlight video. This was Bumble's on-orbit activities. This is how we commissioned Bumble. So this was back in April of 2019, unpacking the robot. This is astronaut Anne McLean, first astronaut to handle our robot. And there's our first wake up. Kind of interesting, you can see how the cameras are affected by the radiation on the orbit. There's all these little dead pixels. I don't know if it comes across in the stream here, but you can see all the dead pixels on the camera. This is the nozzle test. You can see we're commanding the nozzles to open and close. Here's Anne manually flying the robot to collect imagery to build our first map. And here we're attempting to calibrate the IMU. We learned never to ask an astronaut to spin something as fast as they can because she saturated the IMU and we had to do that test over again, spinning it much slower. Here's our first flight. It was pretty exciting. Our first undock. David Saint-Jacques there was the astronaut. He gave us a little sound there for that's not a toothbrush, that's a microphone. Let us hear the prop module spin up on that. Here, David is testing out our disturbance rejection. So he's pushing the robot around, and the robot's job is to stop itself. You can see you're doing a pretty good job. And then this is our first autonomous dock. So you can see here, there's some indicator lights. One's going to light up when we have good connectivity. There we go. Good connectivity with the dock. And this is Christina Cook. She was very excited about this. And then she said, can I do a tumbling run with the robot? This is her idea, to spin the robot and tumble alongside of it. Sorry about the video quality. This is, from space, so our connectivity wasn't great when we were doing this, but it was fun. So we've had some pretty good enthusiastic responses from the crew. They seem to be pretty excited about having these robots on board. So this is one of our longer flights. This is real time. So this is how fast the robot flies. It's about a 10 centimeters per second average speed. So we probably could fly a little bit faster than this, but this is sort of what we consider our nominal speed. We want to stay safe and conservative. And then from here, this is now sped up. This is 4 times speed. This is our first autonomous sortie. So we actually did autonomously undock, fly to waypoints, and then fly back to redock. And then this was our first autonomous survey. So Astrobee is flying to a payload rack, and then this is going to fly a pattern here to image the entire rack. So again, it's 4 times speed.